Hello, this is Pat Kelly. Okay, for this problem, they want us to find the area of the surface over the given region, and they give us this vector-valued function. And what it really comes down to is this formula that you should either know or grab from your book or from your notes. And with the formula in front of me, it even kind of guides me in terms of what work I need to do. I can see that I need a partial of r with respect to u, partial of r with respect to v, and then I need to cross those, find the magnitude, and then put it into this integral. Okay, so let's get started on that. Over here, my r vector partial with respect to u equals 4 I. This looks like it's going to be nice, right? The partial there is 0, and this is also a 0, looking pretty good. And my partial of r with respect to v this time that guy goes to 0 minus 1 times the j plus 1 times the k. So my partials were pretty friendly to me, but no matter what they look like, next I'd want to take the two of them, cross product, and then we'll find the magnitude of that resulting vector. So let me get our set up for a cross product I, j, k, and then the coefficients or the components here 4, 0, 0, across the bottom 0, minus 1, 1. And I'm looking for the cofactor expansion of all this, which will equal, let's do a quick determinant form calculation. My I component is going to have a crisscross here of 0 times 0, 0 minus 0, I guess. That looks good. Minus my j component. Make sure I have enough room here. My j component, I'm covering up that middle column, and my crisscross looks like 4, subtract 0. So I'm just going to get a 4, minus 4. And then plus, and my k component will look like a crisscross here of minus 4 times, subtract 0, so minus 4. Okay, that behaved pretty well too. And the next thing I would do, see if I have enough room right here, just want to find that magnitude of that r partial with u crossed with r partial with respect to v that we just calculated. So the magnitude of this vector here, so I'm looking at the square root of 16 plus 16, looks like 32. All right, so it looks like 4 radical 2 for my magnitude of the cross product. Okay, so now I'll come up here and continue with this integral, or set this integral up. This will equal integral, double integral, my limits of integration. I'll put those on hold for just a second. That magnitude we just calculated was 4 square root of 2. And then the dA, the differential element of the area, is actually pretty easy to handle as just du dv in this case, which then makes me think of those limits of integration. That inner one needs to correspond with u. They told me that u goes from 0 to 2. They told me that v goes from 0 to 1. Now I just want to evaluate this integral. And this one's pretty friendly too, I think, right? 0 to 1, and then 4 square root of 2 times u, which I'll evaluate from 0 to 2 dv. So, I'll do one more step here. 0 to 1. Putting in the upper limit of integration of 2, that's just going to bump that up to an 8 square root of 2, and then subtract the 0. Subtract what happens when you plug in a 0, and that's going to be 0. So you're just looking at that integral now. And if I integrate this guy, 8 square root of 2 times v, that I'll now evaluate from 0 to 1. And since the numbers are so friendly, it's just plugging in a 1, and I get 8 square root of 2. Subtract plugging in a 0, and you still get 8 square root of 2. Okay? That's my final answer. They did mention in the directions they wanted us to use a computer algebra system to verify the results. So if you get a computer algebra system, whichever one you're comfortable with, and put this in, you definitely should be getting that same answer of 8 square root of 2. Okay? Hope that helps.